Okay, so this is a datum. So when, for example, this is a real part, okay, and then the worker do the machining, okay. So when it do the machining, and then there's a datum feature and then part, um, it is actually the this line is actually the simulated datum, okay. However, this one is the surface of manufacturing and certification equipments, and this one is the datum plane and vertical feature, okay. So this is the datum, that which is the reference, but actually in the reality the part would be looks like it would be some rough with some tools, okay. That one, okay. And then in the GD&T and in the dimensioning and tolerancing symbol, if we are using the ESME, we have some symbols, okay. And then it is very important for us to know about this one, and then I have asked the coordinators regarding this, and then you have to remember this for the exam. So for example, so this is the symbol for datum feature. So we're gonna discuss this one by one, okay. So this is the datum feature, which is for the referencing. This is the datum target. This is target point. This is concentricity. If there are two pieces or two shafts that have in one concentricity. This is circularity, keterbulatan, ya. Because sometimes in the part that is made, sometimes it's not really round, okay. So in order to make sure that it is round, it's circular, then there is a symbol called circularity. Okay, this is M is called maximum material condition. I'm gonna explain to you in the I think after few slides. Yeah, this is called free state. This is called tension plate. This is LMC or lower material condition. This is RFS. This is projected tolerance zone. Parallelism, which is parallel planes, and then flatness, cylindricity between, and then this is quite I think we know already. Diameter, the position, all around profile, profile surface, profile line, and straightness. Okay, so as again as in the video that we watched before that, in that actually we gonna learn a lot about the symbols, the referencing, and then how to write that one into the geometric tolerance, and to make sure that every part can fit together and then it can be assembled. Okay, and then here there's a lot of another one. There's perpendicularity, ketegak lurusan, angularity, sudut, run out circular, run out total, counter bore or spot space, and then countersink, depth, dimension, origin, conical taper, and so on. Okay, of course for you especially who doesn't like mechanical engineering, or doesn't like doing workshop things or mechanics things, it is quite new. For me also it was quite new, yeah, but that's fine. We can learn together from the beginning here, so we know the basic for engineering drawing, okay. Even though we may not use it in day-to-day activities in in chemical engineering, but we may need it later. For example, when you want to make your own research equipment in the fourth semester, or in the fourth year, you want to make your own equipment, and then you need to make it and then send it to the workshop. At least you know how to do it. You can also do it by SolidWorks as well, yeah, with the practical. Okay, so let's start from the beginning. Okay, so datum. Datum is actually a two-plane datum reference frame in which the whole is dimension from this is a two-plane datum reference frame in which the hole is dimensioned from left and bottom. Okay, so let's say we have this part, okay, and then this part has a hole that have a bore in it. Okay, so in order to make sure that we can, or the machinist can manufacture the right part that we want. First we have to write the datum first. So we have datum A. Okay, so this just to make sure that this part can attach into to the reference here, okay, to the horizontally. So this is a datum A, okay, and this one is datum B. Okay, so this one is called the datum B. Okay, and then from the picture here there is a hole, and then that's why for the hole we have a symbol which is called the this one, the plus, or the center point. Okay. Okay, to know that where they start the center point, we can have the distance here, for example xx, okay, and also this one, this is the distance with reference to datum B. Okay, so this one is actually the reference from the center point to datum A, and this xx here is the reference or the distance from the center point into datum B. Okay, so with by adding the datum A and datum B, why we don't need the datum, I don't know, for example the other one, for example, why we don't need the datum C, for example, like this, like cut in that one. Okay, I think we don't need that because we don't need more information apart from this one. Okay, so but if you want, maybe if we need the thickness, maybe we can make also with respect to datum C, for example. Okay. And okay, so let's have a look the next one. Let's say how if we add datum C. So the previous one we only have let me write with the pen. So if you look at here, so this is a datum A, okay, and this is a datum B. Okay, if we add the datum C over here, so okay, so if we add the datum C over here, that becomes like this one. Okay, so let's say this is the datum C, and then you can write this is the datum C, this is the datum A, the datum B. Okay, datum C may be needed if you need the the information regarding the datum C. For example, you want to know the thickness of this plate. Okay, you want to know the thickness of the plate, so we have to maybe draw it with respect to the datum C, and then we can know the thickness. Okay, I think this should be datum C. Yeah, this is wait, should be yeah, this one, it should be datum C, and this one is, yeah, this is A. Okay, so here yeah, so we have the datum A over here, okay, and then also B, and then to get the C, we know this is a plate. Okay, but then this one tells you that, okay, so this is actually the axis. Yeah, this is the axis, and this is there is the lines like this, guys, putus tells you there is a hole in it. Okay, so this tells you that it would be okay. So So for the datums, there are 2 or more datums with different priorities, but sometimes the last one is not specified, if not important. But if it is important, then we can also write it like this, okay? Datum-datum yang dengan prioritas yang tidak dinyatakan secara spesifik. So the last one, I think the datum C is not a priority, for example, but for this case, we write for the first priority that we have to see is datum B, and then A, and then C. Okay, so and then let's try to imagine this one. Okay, maybe wait. Let's watch this figure maybe for a minute, and then try to think about how can you transfer, or how can you transform this assembly into here. Okay, give wait for 1 minute. So let's have a look, and then let's see. Okay, if I close this one, this one, my right hand side, do you think, can you imagine how the specimen looks like? If I close this one, oops. Okay, so from here, for example, this is like a vertical section view. Yeah, so this one is actually the vertical section view over here, or maybe over here. So sorry, from over here we look at from this point. Okay, so we see that there is a plane. Sorry, there is a part over here. Yeah, this one is tell you this part, and then from the front we can see also the shape is like this. Okay, with the same with this one. Okay, from the front, if there's nothing inside, we can't see the hole, but from the top side we see that there is 2 holes with some there are center points there, there's an axis there. So here we can draw that there's an axis and there is a hole inside it. Okay, and then this one is with reference with datum A. Okay, so this is a datum A, so this is actually the this A is actually this one, or the primary datum plane, and then I can write that it is a datum A. Okay, and then we can solve that from the top. Yeah, so if we look at it from the top point of view, you see that there is this part and also that part, and also the circle. Okay, the hole, and then with the center point, and even the center point has the line, which is all the center point are coaxial with each other. Okay, and in order to know the length, we can have a distance. We measure the distance between the first center point with the datum C. Okay, so this one is gonna be the datum C. Okay, so the length from the first center point to datum C is 10, and the length from the second center point to the datum C is 50. Okay, and then in here from the top we see also datum B, so this is called the datum B. Okay, so datum, maybe I can write that the datum is actually the reference plate. Okay, and then if you look at the referencing here, this tells you that there is a symbol of this one, and this symbol tell you about the center point. Okay, so this is the center point. Okay, and this and then this is tell you that 0.2, which is the tolerance is 0.2, and this is M, which is called the material maximum condition, maximum material condition, and with reference to datum A, and then the second one with datum B, and then the third one is datum C. Okay, let me stop it here. Do you have any questions? No? Okay then. Let's have a look at the next one. Okay, so for example, this one just tells you that how to write this one, yeah. So sorry, this one is called the center point. And then if you look at in the previous slides, there are so many symbols. There are so many symbols here. There are datum features, concentricity, circularity, and so on. So we're gonna learn all of this, and also perpendicularity and so on, and then one by one, and how can we place them into the feature contour flame like this. Okay. Right, okay, so this is also, for example, if there is a plot like this, this one is the concentricity, this is center point, and then it can be also like this center point. Okay, now let's talk about geometric tolerance. Geometric tolerance can be in the form, it can be form, shape, the orientation, the location, and the runout. Okay, so the tolerance is actually the maximum allowable value in form of deviation, and then the form tolerance limits the deviation of a feature to geometric ideal of a line or a surface. Okay, and then this geometric tolerance should be fit on each other, so when all the parts are assembled, we can fix them without hassle. Okay, because sometimes if if we make a shaft, for example, which is the tolerance is so a little bit bigger, or if we make a larger diameter of you know, the shaft, for example, and then when we make just with small hole, then the shaft can't go into the hole, so that would be you know, we have to refit again and then redo the production and then check it again, so it is gonna be spending much time and money. Alright, so so the tolerance, the form tolerance limits the deviation of a feature to the geometric ideal of a line or surface, and in a spatial, for example, the tolerance for in the line form, the garis, for example, straightness, kelurusan, and roundness, kebulatan, or circularity, and spatial for surface, for example, flatness, flat, yeah, the and then planarity and also cylindricity. So let's watch one by one. Okay, so let's have a look, and then we also have orientation tolerance, for example, parallelism and perpendicularity. Okay, so after this I will be explaining lots of geometric tolerance from the beginning, and then if of course when you hear it first time, it would be such a lengthy slides and a lot of new terms that you're gonna learn, but yeah, but that is, yeah, we actually study to we learn something new, and then we can use it for our project or for our assignments and so on. Okay, so just be patient, and then let's learn one by one. Okay, and then here we also have a location tolerance, for example, coaxiality or symmetrical. Okay, and then we have a run out tolerance. It's actually the part of orientation, and tolerance the location just because of specific measurement method, but it is defined as its own type of tolerance. I'll explain to you in a sec about the run out tolerance. Okay. Okay, so this is the term that we I think this is for additional notes in Indonesian for all the classes, so I'll just put it here so you can all read it. So we have 4 geometric tolerance that doesn't need datum: kelurusan, straightness, kerataan, flatness, kebulatan, circularity, and then kesilindrisan or cylindricity. Okay, the other tolerance datum need geometric tolerance need datum. Okay, so the difference between kelurusan, straightness, and kerataan or flatness, and also kebulatan, cylindricity, kebulatan, circularity, and also kesilindrisan. It's actually based on the geometrical dimension. Okay, so the straightness and the circularity is actually 2-dimension, while the for the flatness and also cylindricity is actually 3-dimension. Okay, so let's see one by one. Okay, so this is a straightness atau kelurusan. Okay, let's say we have a shaft. Okay, and this is the shaft. This is from the sides, and also this is from the front. Okay, so from the front, in order to know that it is a rod or tongkat ya, bulat panjang like this. Okay, first we know that it has a center point like this, and also it has an axial like that. Okay, so this tells you about the center point. Okay, and this one is the axial line. Yeah, the axial line. Okay, and then over here it has this symbol like stripes like this, and it's called flatness. Sorry, straightness. Straightness 0.005, while here the diameter is between 0.5 and 0.45. Okay, in the rectangle. Okay, and then now we have a rectangle like this, and then like a bar. Okay, like that. Here we have the it's not the diameter, but the distance is 0.5, and then this is the straightness, kelurusan. Okay, so even if we draw it like this, but in actual, sometimes in actual profile we can see like this. Okay, it can be the product is actually would be okay, as well as we have the tolerance about 0.002 tolerance between those lines. Okay, if we have higher than that, then it is actually not on spec. Okay, so but actual profile, the actual profile, it is okay if we have fit like that, as long as it is inside, near, below the tolerance. Okay, for example, about the toys that I said before about Legos, maybe in Lego there are also like this, but very small, maybe in microns. And then if it's very small, I think that should be fine. Okay, but if you have a really large tolerance, which is more than the allowable tolerance, maybe it would be not good for that. Okay, for the inspection method, how we know that we have a straight line or not, we have a straightness or not, we can first we will put a bar like this. This is to measure that it has a straight line or not. Okay, so in a rod, this is called rod, this is called slab. Okay, so in a large rod like this, we check it with this one. Okay, so if it is not flatness, of course there would be some room missing, or like a hump like that. Okay, and then in here, for example, we have a slab, and then there's a inspection method would be around this area to make it the straight line. Okay, so that is the straight line. So the one that we're gonna learn here, in each symbol there are there is a explanation what it is, and also what this tolerance means. And then as long as we make the parts around this tolerance, that is still fine. Okay, this tolerance give some space to the machinist, to the worker people, or to the workshop people, to make the the equipment or the part that we needed. And also when it is assembled with others, it's gonna be okay, safe, and have function. Okay, a higher tolerance means give rooms to the machinists, or to the the worker people, the workshop people. But the lower tolerance that is needed, of course, it will requires more technological and more precious equipment, and maybe it would be the more expensive. Okay, so straightness usually has two different functions depending on the how it's called. In normal form, it's called a surface straightness. The tolerance that controls the surface straightness. Form a line somewhere on the surface feature. So if, for example, if this is the real question from Aska. Okay, Aska, do you want to have a question, please?
Yes, I have a question for the previous slide.
Yeah.
There's a cylinder and then there's a rectangle. Which one is the? I don't understand which one is the actual object. Is it the on this one on the left, or the circle, or the?
Yeah. So
which one is the actual object and the reference?
The actual object is this one, the green one.
How about on the drawing? Which one is that?
This one, if we have the rod like this, the way we draw it is this one. Okay, so this actually, if we look at from the front, we only see circle, right? And this circle will have a center point, and this center point is written by this one. Okay, so this symbol, if we have this symbol and then we look at from the front, it is a circle because it has a center point. Okay, now let's look at from the other this side. From this side, if you look at from this side, then it looks like a like a rectangle. Okay, for example, let me open. Okay, I have a bottle here. Yeah. Can you hear my? Okay. Can you? So for example, for the rod, if you look at from. Okay. Can you hear me? And hello.
Yes. Now we can hear.
Yep.
Oh yeah. It is mati lampu. Okay. Right. Okay. So this is the the rod, right? Okay, so this one is from the front. Okay, so like from the front, you know that it is a circle if it has a center point. So that's why in here you have the center point. Okay, even it is not written in here, but we know that it is a circle because it has a center point there. Okay, and then this one is, if we look at here from this side, like that. Okay, if you look at here from this side, we only look this as a rectangle, isn't it? Like a block, kayak balok. Okay, because it's like persegi panjang. It's not like rectangle, but it is like a persegi panjang. Okay.
Okay, I get it.
Yeah. Okay.
One more question.
Yes.
Since 0.002 is the tolerance for straightness, what is the 0.5 and 0.495?
Okay, so
what is that for?
0.5 and 0.495, this one is actually the diameter. Okay, so this is the actual diameter, which is the actual diameter should be between 0.495 and 0.5. I don't know about the the unit, yeah, maybe inch or millimeter, yeah. Need to check that one. But actually, if this is actually the diameter. Okay, any other question?
So does
Oh,
that mean
thank
like
you.
for the second one, for the rectangle,
Yes.
that is the diameter of the block from left to right?
Yeah, so okay, I have this T over here, yeah. So for this one, that would be the distance, yeah, distance, this one, okay. I don't know why they put it still the diameter as well. I think this is, I don't know if it's just because we put it the same with this one, but or because it's that diameter, yeah. This is a distance.
Oh, okay.
Yeah, this is,
So that was just a slight mistake then.
yeah, yeah.
Okay, I see. Thank you.
Okay. Okay, let me continue this one. Okay, so this is this surface straightness. So it in its normal form, or surface straightness is a tolerance that controls the form line somewhere on the surface or the feature of the feature, and also it can be made as an axis straightness, as a tolerance that controls how much curve is allowed as part of axis. Okay, so for straightness, kelurusan, okay, this is the symbol, yeah, this is the symbol of straightness, and then this is the tolerance. As long as the tolerance, or as long as the surface it has a flat of a straightness, like between 0.1, it is okay. Okay, for example, and then for example, this is a rod, and then this is the diameter 10 let's say it's inch, yeah, let's say it's inch, and then this is the tolerance. So as long as the diameter is 10 inch plus minus 0.5, that's fine, and it need to have kelurusan straightness 0.1. Okay, because what happens if we have something like this, but maybe it looks slightly larger than that, for example, yeah, like larger than the tolerance, what happens is when we need the shaft and then we want to make the assemble with the next part, yeah, for example with the hole, maybe this part won't fix with the hole. Okay, so that's why we have to measure, for example, for this shaft, it should have some type of straightness. Okay, and the straightness is actually about 2 dimension. Okay, and later we're gonna see about the what is called the flatness, which is about a 3 dimension. Okay, so here's is the straightness of the axis. So the previous one is a straightness line, and this one is the straightness of the axis. How we know that the axis the axis is actually we have a good straightness. It looks also like this. Okay, so this one, this is the dimension. This is the diameter, and this is the axis. Okay, so in reality, sometimes the axis can mix like that. Yeah, it can the true axis or shaft, sometimes it can there would be some bending or something like that when they make it, or maybe, yeah, just make it bigger. Okay, so the inspection, we can use, we called it phi block inspection, which is located on the true axis. So there is some indicator to check about the position, or the inspection method is using a functional gauge. Okay, or if we put this shaft into the functional gauge, if it can go inside this one, it can fix, for example, with, of course, with the right direction, similar with the go and no go gauge. Yeah, if we remember a few weeks ago, then it can pass the inspection. If it is gets stuck, for example, so that means it can be so it is not working properly. Okay, I remember when I did my PhD, and then I went to I need to make something like this. I got this one. So actually I got I have to buy alumina cylinder, okay, and then I need to put it in a furnace. So this is, for example, the furnace. I think I explained to you last week. And then I need to put like some alumina furnace, and then need to put my sample here. I need to heat it up, so I need to buy this alumina furnace, alumina tube from Russia or from Germany, from something like from China. And then when I put it here, when I'm actually insert them into the furnace, it gets stuck, you know. It's not pass along that one there. So when I check it, it's actually my alumina tube that I bought is actually bent like this one, okay. So because why? Because sometimes it can be like this, okay. So the straightness of axis, this tells you that it can be the axis can be okay, yeah, it can be straight. So an equal rise in opposing element can mean that the axis is right, but it is not good as well, right? So that's why we have to measure the straightness of axis and also straightness of the surface as well, okay. Or it can be like this. This also the axis is okay, it's straight, but there are equal opposing in elements, okay. But of course it's not really good to our specimen. Or it can be like this. If this is like this, that means it is not the axis is not straight, okay. Or this one also is not straight. So in the some parts that we make or we know from the machinists or from the workshop people, that can be like that, okay. And then the problem is actually later on when we try to assemble all those parts, and then okay, why this is get stuck, and then okay, this is because of some of the straightness. Okay, so back to here, there are two types of straightness: straightness of the surface and also the straightness of the axis. Okay, using the V-blocks inspection. Practically, I didn't do it myself, so I think let's wait until the practicum. I think there should be the assistants and the coordinator will also explain to you about how to measure this one, especially if the practicum is on the campus. Then you should be introduced with all of these type of equipments and how to measure those straightness of the axis. Okay, and then this is the additional notes also from the coordinator. There are two types of straightness, jenis kelurusan, lurus permukaan, the straightness of the surface, and the straightness of the axis. I think we know, we have learned this before, yeah? Okay, so the next one. The next one is circularity. Okay, circularity or kebulatan. Okay, even though we claim that we have a circle in here, okay, practically when we have when we have the machined parts, sometimes it can't be a perfect size, so that would be some roughness and something like this. Okay, so circularity is noted by this circle, okay, like that. Okay, it is actually the tolerance for the circularity. Okay, let's say we have this this rod again. Okay, so this tells you about the tolerance for the diameter. And this one, there's a circle here. So this circle is actually not the straightness, sudah bukan tentang kelurusan, but this is actually shows you about the circularity. Okay, and then this is the tolerance in it. Okay, so at least that even though the black one is the, I think we make it really, just an example, yeah. If we have the black one for the circle like that, when we machine it, and then that's the real result. As long as it lies between those tolerance, between 0.02, not this, of course it's not the scale, then it is still okay. Okay, so the circularity symbol is used to describe how close an object should be in a true circle, because sometimes it can be a little bit, you know, bent, or it's not really circle. Yeah, it can be maybe a little bit make it ellipse or something. Okay, the circularity, or it's called roundness, kebulatan, is actually two-dimensional tolerance that controls overall form of a circle. Oops. Ensuring that it is not too long square, or that one. Wait. Okay, what happened? Wait. Okay, yeah. Let's go back. Yeah, so it's two-dimension tolerance that control the overall form of a circle. Okay, and how we make it, how we inspect them. So at one slice at a time, there is a gauge. We call it a precision slide, and we move around the parts, and this tells you about how the parts, to check if it's a circle or not. Okay, I think if it is circle, the indicator should be similar. Okay, because the jari-jari, the radius is actually would be similar. But if it is not a true circle, there would be a plus minus into here, the Noto scale. Okay, here, so this is the circularity. For example, we have again the rod, and this is the center point with the dimension, the diameter of 10 plus 0.2, okay, with the same resulting condition, and then we allow the tolerance for circularity is 0.08. So that means in 1 point there, it is maybe allowable for the circle can be shaped looks like this. Okay, it can be looks like this, but as long as it is between 0.08 for the tolerance, it is still fine. If it is more than that, then you can't, you have to, you have to machine it again to make it maybe smaller with that. Okay, so and then the next one is flatness. So if straightness is a two-dimension, so if straightness is two-dimension, kelurusan, so flatness is three-dimension. Okay, flatness, kerataan, yeah, it is three-dimension. Okay, so for example, I have this plate. So if I draw this one, it's gonna be looks like that, and then there is a circle there, and then maybe it will have some thickness over there. Okay, and then we were interested with the surface flatness of this one. Okay, so here this is a datum for that one, yeah, from the top, yang di depan, yeah, from the front, that one, and then this is the surface of the flatness, like that. Okay, jajaran genjang, yeah. Okay, and then the surface of flatness. Okay, so the point, even the tolerance, although the surface may be a little bit rough like this and have a tolerance 0.002, it is okay as long as it is within the tolerance plane zone. Okay, and if we maybe, for example, want to put this part on top of others, like in the previous videos, we also can do that. Okay, it won't cause any damage. Okay, so flatness is a form of a control. The flatness control defines how much surface on the real part may vary from ideal flat plane. And then the tolerance zone is actually the flatness tolerance zone, is actually the volume. Okay, the volume between the two parallel plates. So we imagine that there are two parallel plates, and then the distance between the two parallel plates would be around 0.02. Okay, and then it is the flatness is the distance, the maximum distance between the two imaginary planes. Okay, and how to check it? So if we have some parts, here we have to check with some indicator as well. Okay, so maybe we can put some leveling fit over here. So if this is the part, so this indicator will move free on all of the surface to check the flatness in 3 dimensions. Okay, if you look at the first one in straightness, they only look at the one line, but in flatness they look at all the surface. Okay, so here this is the flatness tolerance zone, the volume between the two parallel plates. So as long as the volume, the round or the roughness is between those two imaginary plates, that is fine. Okay, similar to flatness, in roundness we have cylindricity, kesilindran ya. So if we have circularity in 2 dimensions, we have cylindricity in 3 dimensions. Okay, so here the cylindricity, this is the symbol. Okay, so this is the cylindricity like this. Okay, so this is drawing, and that means that we have this rod, and this rod has a diameter minimum 0.495 and the maximum is 0.5, and it should have cylindricity tolerance of 0.002. So all the volume tolerance, it should be within the thickness, the different thickness difference of 0.02. Okay, so again, and this is how to check the inspection using this is the indicator or the precision slide to check the roughness or the cylindricity of the surface. Okay, so cylindricity is a 3-dimensional tolerance that controls the overall form of a cylindrical feature to ensure that it's round enough and straight enough along the axis. Okay, so cylindricity independent of any datum feature of tolerance needs and to be less than the diameter dimensional tolerance of the part. Okay, so that is cylindricity like this. Okay, so you can see this one is actual. If we make the rod, it may be possible that the part that we make can have some damage, cacat, or it's not straight like this. It's not straight, also it's not round, and so the combination of that in 3 dimensions is called cylindricity. Okay, and then the next one is parallelism. Yeah, parallelism, or this is the symbol is like that, like 2 parallel lines. It is to make sure to check between two parts. Okay, so if we want to check between 2 parts, it is called parallelism. I think we can see this one. Yeah, I think this one this is an example. Again, to check the parallelism, we can use the similar inspection method, for example, for flatness or straightness. But I think the a good example of parallelism is with this one. Okay, so we have 2 hole like this. Okay, so this one is a bigger part and this is the smaller part. You can see that maybe this is from the top side, yeah, and then this is from the sides. Okay, from the top side we can see that there's a hole like this, and then there's a circle with the hole, with this is the center point, and then this one is also with this center point, and this is the datum, and we know that this center point is actually parallel the line, yeah, is actually, because this is the line, okay, the axis is actually parallel with this axis, okay. So how we write it, for this one, it is with the part of datum A, so this is the circle, and then this is parallel, this is the parallel lines, okay, and then this is 0, 0, 2, and then maximum material condition, and then with datum A, maximum material condition. Okay, so here, you know, the this one, it's actually, yeah, this is an example that how we make sure that these two shaft is parallel. Okay, in the previous one we can see the previous one, for example, if we want to know that this axis should be parallel with this one, okay, we can also make also that yeah, this should be parallel with that one, okay. All right, okay, and the next one is perpendicularity, ketegaklurusan. So sometimes when we make things, yeah, for example, we want to make this blue one, okay, the blue part, okay, and this blue part we need to put it with the other red part, okay. If it has a good perpendicularity, sometimes one object can be stuck with each other, okay. So that's why we have to make sure that we have perpendicularity with also a little bit of some bonus tolerance. Okay, so in elementary geometry, the property of being perpendicular or perpendicularity is the relationship between the two lines which are meet at right angle, 90 degrees. The object extends to others related to geometric object, and a line is said to be perpendicular to the another line if the two lines intersect at the right angle. Okay, so perpendicular, we make sure that if we connect the two parts together, we can stuck with each other, and also it's perpendicular to each other. Okay, so for example, we have this part, okay, and then we have the shaft, and we have the hole like this, the axis, and we want to make sure that this flat, the flat or the right over here, it should be perpendicular to the datum A. Okay, so this tells you that the center point or this axis should be perpendicular to the datum A, yeah, with the datum A, and the tolerance is 0.02. Okay, if you have a slightly missing 0.02, still inside the tolerance, that's fine. But if it is too much, then the part that you're making, you can put it over there. Okay, maybe for you, yeah, we will only try to draw it, or try to you know, to just watch it, or try to understand and then do the exam. But our friends in mechanical engineering or in aerospace engineering, they make this up to the material, okay, they make the prototype, okay. So so in order to do that, they have to make sure that the drawing is okay, is comply, and then the part that they make also you know, okay. Okay, and then this one, angularity, tentang sudut, ya. This is the symbol to describe the specific orientation of one feature to another at a reference angle. It can reference two dimension to the element, but commonly related to the orientation of one surface relative to other datum planar. For example, this one, should be, so we have this part, and this part should be 90 degree, okay, with related to the datum A. However, this one, we can have the tolerance around 0.030 degree. Okay, so as long as we have maybe slightly a little bit bigger or slightly a little bit smaller, as long as it is the tolerance in the range of 0.030 from this, it is still okay. All right, so this one, yeah, this is some part, yeah, this is one here. So if we have this type of question, or this is the specimen or the parts, this is how we look like from the front over there. Okay, we can't see, we only see this trapezium shape. Okay, but we know inside here there is a hole, so there is axis, and also the you know, the lines, garis putus-putus tells you about there is a hole. Okay, and because it is chopped like this, and then in angularity we have also the angularity with the tolerance 0.02 with respect to the A, or the datum A. Okay, this one also similar. For example, this one actually 30 degree would be that one. Okay, and then this one is the profile of a line. The profile of a line, this one is actually, again, it is a quite a 3D dimension profile of a line. For example, if we have this line drawing like this, but actual it looks like this one, the profile of a line is like that, yeah, the curve symbol. Okay, so it is okay as long as it is between the tolerance zone. Of course, it's not to scale, yeah, so it would a little bit missing like that. As long as it is within the tolerance zone, that is okay. Okay, the inspection method is using this indicator as well. So we inspect only one slice of the cross section at a time, like this. Okay, in respect to datum. Okay, and then the profile of the surface. So the line is actually the 2 dimension because in only one slice at a time. So one slice at a time, so that means only a straight line, or maybe only a line. That's why it's called profile of line. So it is a 2 dimension. But however, the second one is profile of a surface. We try to check it in a 3 dimensions. So we inspect all the point on the surface vertically and horizontally, so it looks like the volume or the 3 dimension. Okay, so even though this is the real, yeah, this is the real, the black one is the real, and the imaginary one is the pink one. So as long as it is between the pink one, between the tolerance zone, it is still okay, and it's still on specification. Right, so there are so many parameters that we learn, yeah, but that's why it is for this week, yeah, this hour we have to learn all of them. Okay, and then the another, this one is called the concentricity. Okay, concentricity is we have to you know, circle or to cylinder part together like this, which is the concentric diameters with dimension. So this is 2, for example, and then this is 1. Okay, I once have example about this one at the workshop in my university. At that time, I need to make some punch or the you know, equipment to make a palette for my powders, and then he make like this. So first he make a circle, I mean a heavy cylinder. Okay, and then he make maybe something like that, maybe as a dasar, yeah, of that one there, and then I make a punch like that. Okay, so I want because I need to make a palette, powder palette, you know, like a tablet, yeah, but at that time I don't have a powder a powder or a tablet machine in my university. Okay, but I need to make a powder or powder palette. So what I what I do is actually I went to the workshop and then asked the mechanical guy over there, can you make equipment to make for me to make pellets. Okay, I'm gonna make it, he said. And then I remember his name is David. And then he make the over here like very close like this, yeah, from the bottom, and then put over here so I can put some powders over here, and then close it with some you know, a cap like this, and then I punch it with hydraulic press so after that I can get some, you know, very thick powder after that. Okay, so in order for them to make this one really smooth, so he make the, at that time I don't know really well about making this engineering drawing, so but he make the sketch, even it is manually. Okay, Winnie, do you want to make the equipments to make your tablet, you know, to make the pellets for your experiments? Yes, yes, I said. And then yeah, he make it, and then I'll try it using the hydraulic press, and it is worked fine. Okay, and then this pellet I use this as a, you know, as a reactant for my experiments. Okay, because I'm using this reactant for the experiment for making magnesium metal from ores, yeah, from ore BG. Okay, so this is typical of concentricity. This one, okay, the symbol is circle like that, or maybe like that, yeah, the circular thing. Oops. Okay, so this is called concentricity, not circularity, sorry, concentricity, which is a complex tolerance zone used to establish tolerance zone for median points of cylindrical or spherical part of a sphere. So concentricity is generally reserved for high pressure system part only when there's need to control median point. So if this is the two parts should be in one axis, yeah, and then should be in one concentricity, maybe it would be look like this one. Okay, so so this one is concentricity, the drawing, and also the some tolerance zone. Okay, and then this is how to measure the inspection method, the tolerance zone, to make if two parts has a you know, the one concentrate. Okay, and then this is a circle run out. This is called run out. Okay, so what is run out? Run out tolerance is used to control the location of circular part outside, because in circularity is actually control the roundness, but in round out it is like about the apa ya, miring ya, like it is make, for example, larger. Okay, so this is called a run out. We check it that one. Okay, so circle run out merupakan toleransi seperti kebulatan namun memiliki datum. For example, steel velg on a bike, a motorbike, or spurring ban mobil. Okay, so this is a run out. Okay, so this is the circle run out to check with the datum over here. Also, the inspection method is also similar with circular reading like this, with some indicator the maximum. Okay, so for you, you know, of course, curious about this one here. Hopefully, with the practicum, you can see the questions or the how to reading, or maybe you can watch video, found the video on YouTube, yeah, to how to measure this one. Should be I think it should be somewhere in the YouTube as well, because it's pretty basic courses for mechanical engineering, for any engineering, or for civil engineering. Okay, so here also, for example, that's why if we try to combine all of them together, at least you should know what is looks like, yeah. So this is, for example, run out, okay, this one, or this is the both surface. Yes, this is just some example. Okay, and then another one is position. Okay, position tells you with center point like this. Okay, for example, we have this bar over here with a rod there, and then it should have some position, and then we can't miss the position, because if we're missing the position when we stuck it with other part, it won't fit together. Okay, so this is the drawing. Okay, this one, and then with the datum A, B, and C over here. Okay, and then we to check it, you can use a functional gauge to check the inspection. Okay, this one, for example, is quite large over here, so we can see it here. Yeah, so for example, this tells you about this is datum B, the whole of B. Okay, and this is a datum A, yeah, which is on the over here. Yes, datum A. And then here you can see that we have the position. Here the position, we write this as the center point, and the center point would be okay as long as the tolerance is just 0.05. Okay, so for example, we want to check the position location from the whole from the center point over there. Okay, this one, so this one also, for example, the datum also, while it is only in the flat surface, the datum can be on the surface of the cylinder, if any. So it is pretty much common part in mechanical engineering. So if this is, for example, this is the datum, and then this is the distance. Okay, if the part looks like this, but yeah, it looks like two cylinder, but a little bit chopped over there. Okay, and then this one is the you have the center point, this, and then also you have the tolerance on the diameter over here. Yeah, the diameter over here 0.005 with maximum material condition. Okay, and then again the symmetry. Okay, for example, this is symmetrical. We have to do symmetrical just in the middle. This one is how to write it, also with the center point and also the tolerance, and then with the datum over here. This one, the tolerance cylinder, can become slot shape if one direction depart from MMC more than another. So this is we can also write the symmetry like this. Okay, so anyway, there would be a lot of variation on those geometric. We can check one by one, and then so this is the general geometric tolerance. It can be revert to ASME, or in this case is revert to ISO. I think this should be quite similar, and again similar to the linear tolerance. We have like there is a number, there is a alphabet over here that tells you about the class and also the the number. Okay, so for example, the ISO, this is the code 2768MH. M menyatakan the general dimensional with class M, and capital H shows you about geometric for class H. Okay, so there's dimensional and also the geometric. Okay, so here we in each so we're gonna revert to ISO. In the previous video we revert to ASME, but in this case just revert to ISO. Here we have all the characteristic: flatness, straightness, roundness, parallelism, and so on. And then to know that what is the maximum allowable tolerance, we can look at all the tables. Okay, so rather than you put the tolerance, you can write the alphabet here to make sure that what is your class geometric types, similar to the linear tolerance that you learned last week. Okay, so here also you can see that also that the tolerance class, and then it always depends on the length. If it is more than 1000 millimeters, then the tolerance class would be such like this. For example, it is more than 1000 millimeters for tolerance class L. The tolerance of the straightness, yeah, the gap, if you remember, would be 1.6. Okay, the perpendicularity, there would be some tolerance as well, so you can have look. For example, maybe I can let's draw okay, so for example, if you have the straightness or the flatness, and then you have those tolerance, okay, so like that. Okay, so that is the tolerance. Okay, so your tolerance, it depends on what class and also the nominal length. Okay, so they the workshop worker will know how the machinists will know how can they apply the tolerance based on this ISO. This is also similar with perpendicularity, and then there's also tolerance for symmetry, circular round out, and what else, and so on. Okay, right. Okay, so this is a very very detailed. I don't know, hopefully we can have some more exercise about this one, but yeah, for example, this is a typical part, and you can see that there are number of codes over here. So then when they assemble together, it is would be okay. So I think this one is very I think it's not really clear. Let us check with different books, yeah, for after this, after we finish the slides. Okay, so anyway, so the geometric deviation is affected by 5M, the material. Okay, how hard is the shape or the rigidity of the material, and the stress of the material. If you work with steel, it is quite ductile and then quite easy to shape. If you work with titanium, it is very hard to machine, so it is difficult to find precision that you want. This is also the machine, the precision, the rigidity, and the thermal, and also the vibration. Maybe you watched some video last few weeks about how we machine something, and then so it depends on the machine, yeah, on the machining, and also the method. If it is the tools, is it automatic? Is it using laser, or is it just manual chuck, fixing, and clamping, and so on? And then how fast it is cut, and how deep is we cut that one. And then the measuring device when we do the inspection and checking, and also the manufacturer, okay, the skills, and also the environment that we use. Okay, so each machine and each production floor will have specific capabilities in geometric deviation, and it is the roles of quality control and quality assurance in that production department that will need to make sure that the products that we make or the part that we make should comply with standard. Okay, for example, we have the department or the plant that manufacturing plant that produce motorbike, for example, yeah, in Bekasi or in Karawang, for example. Okay, so how we make sure that all the parts can fit in together, it based on the quality assurance and the quality control later on. Okay, I think our friends in industrial engineering or in manajemen rekayasa, yeah, in the engineering management, they also knows a lot about how to inspect the quality in the production floor. Okay, but for us in chemical engineering, we actually more about the commodity, about foods and so on, and it's not for manufacturing part. Okay, so okay, and then last one, it is about the tolerance zone. So we have these types: maximum material condition, least material condition, projected tolerance zone, and S, or regardless of feature size, of RFS. Okay, so in GD&T, maximum material condition is a feature of size that contains the greatest amount of material yet remain within tolerance zone. For example, we want to have the largest pin diameter, largest shaft diameter, okay, or smallest hole size. That is called the maximum material condition. Okay, the least material condition, if you have L over there, is actually condition when I think converts to that one, which is the least amount of material exists within the dimensional tolerance. For example, the smallest pin diameter or the largest size of hole. Okay, so the call out also override the GD&T rules number 2, which is regardless feature of size rule. Okay, projected tolerance zone, it is a final dimension which is subject to assembly tolerance stack up. Okay, and then this regardless feature of size is the default condition, a tolerance, a GD&T, and requires no call out. Okay, so it's about the controlling. Okay, so this one, so this is also, for example, like we know that in the video in the beginning that the function of dimensioning and tolerancing is when we combine them together, they can fit perfectly. Okay, so sometimes they have to write this one, for example, straightness, this is the maximum material condition, or this one is lower material condition, for example, like this, and so on. Okay, would be like that. Okay, and this one, for example, we have a shaft, and actually this is the hole. If this is the external feature and this is the internal feature, and for example, we have this is how we write. Let's say if the external feature like this, a little bit mengecil sebelah sini. Okay, so in order this external feature can fit into the hole, we have to write this LMC over here, which is the hole is very large, yeah, because lowest material condition. So the hole is very large, and over here MMC, because we have a smaller hole. So it's actually larger hole is lowest material condition, because a bigger hole means less material. Okay, and the smaller hole is called MMC, or maximum material condition. So that means all of your material are there. Okay, so you have smaller hole. So this one. Okay, in the video that in the link that I put on the EduNext, there are a number of videos from the person there to explain more about this one. So I really suggest that you watch the video and then have a look at that one, yeah, rather than seeing from this presentation. I think I personally think that watching some of example from the video is actually much better to understand. Okay, and then this one to check the to measure the MMC, maximum material condition, you can check using go or no go gauge. Okay, so to make sure that you have the larger shaft, for example, over here to check. Okay, and this one to measure the lowest material condition, we usually check the using micrometer screw, yeah, screw micrometer. Okay, this is just some additional about MMC concept. So when the part of feature contains maximum amount of material everywhere, so this is actually quite similar. Okay, for non-cylindrical component or the flat component, how to measure them, we use like two, there is two flat object like this to make sure that it has a similar straightness, yeah, to check it like this. Okay, and then for non-cylindrical component here, we use a micrometer to check the LMC, and then use a dial gauge like this to check the to check the MMC over here. All right, looks like this one is the end of the slide, but before that, I would like to let me stop share here, and I would like to explain to you about the book that we use. Okay, before that, so let me check. Wait. So let me open my file first. Give me a second. Okay, so wait. Open. Okay. Okay, so I'm using this book, Madsen and Madsen. Wait. Okay, so I'm using this book, Madsen and Madsen. It's fifth edition. So you can see here over, maybe I can make it bigger like this. Okay, so this is the dimensioning and tolerancing in chapter 10, yeah, this one, the dimensioning and tolerancing. So more about that one. Okay, and I'm not sure, I need to check with the coordinator. Maybe next week we're gonna have just assignments about how to draw free hands, yeah, using free hands, this one. So if you look at the book Madsen and Madsen, okay, I can write the references. So from the beginning we learn about the introduction, okay, to engineering drawing and design. This one, okay, which one? This one, yeah, introduction to drawing, engineering, design. And after that we learn about the units, yeah, about the units, and also the there. And then last week we learned about should be about dimensioning, yeah, but linear tolerance. Okay, and then there's some application, and then now we learn about dimensioning and tolerancing. So all the symbols, the components, yeah, all of them are here. Okay, so you need to, if you need more explanation, or want to expand your knowledge. And I think this is very useful for me, for you as well, because this can you can put this into the SolidWorks, right, when you make your lab, and also when you make things. Okay, and then here and then also for the CAD application which you dimension, and then also there are a dimensioning system and so on. Okay, so have a look later on. Let me open again the book. Okay, so this is the book, Madsen and Manson, Engineering, Drawing and Design. All right, now any questions, anyone? No? Okay. I know it is looks like remembering or something to try to understand, but so yeah, in the exam looks like it is gonna be closed book, and you have to understand what is the symbol, and then how it's done. So let's try our best, and then try to remember and also understand all the symbols as possible. Okay. All right, I think that's all from me now, and then thank you very much. I'll see you again next week, and then have a good day.